Okay, so that should be working. Okay, awesome. Okay, awesome. So we're gonna jump right into doing machine learning this module. So we will be talking about a type of machine learning called unsupervised learning. And in particular, we're going to be using a technique called principal components analysis. And so there's a video in the pre-module video I was going to have y'all watch, but you can just watch it after because of, no permissions to get to access it, I think. But basically, the idea of it is, or the actual math behind it is pretty complicated. Also, can I get a thumbs up to make sure people can actually hear me? I'm assuming people can, but I figure I
Yeah, we
might
can
as
hear you.
well. Okay, awesome. Thank you. So the math behind it is really complicated, to be honest. Like, I have no intention of fully understanding the math. But the actual like way it's used in data science isn't too complicated, so that's why I really like talking about it, and it's really common. So has anybody actually heard of principal component analysis before? I'm not sure if something that gets talked about outside of college data science courses. Okay, it doesn't look like anybody has heard of it before. That's totally fine. I had not heard about it until I started taking like junior level, like a I don't know 100 or 200, 300 level data science courses. So it's definitely not something that I think most people know. But the idea of principal component analysis is that if you have a data set with a lot of statistical features, like we have with multiple particle tracking, and you want to visualize the whole data set and see if there are any trends or any clusters of data, you can't really do that with like 35 features, right? You can't just get a visualization in 35 dimensions. So the idea of unsupervised learning and in principal components in particular is that we can reduce the size of the data, reduce the number of features in the data down to a smaller number that still captures most of the variance and the most of the key parts of the data, while also being able to visualize it. So taking it from X number of dimensions, so usually 10 to 30, 10 to 100 even, just any high number of dimensions, and reducing down to 2 or 3 key ones that we can then visualize. So again, we probably won't touch on the math too much. There should be some math in that video if you want to learn more about it. But yeah, first we're just going to figure out how to kind of make some plots with it and get some insight. Okay, so I think first thing we'll need to do again is pip install diff predictor. And yeah, if anything comes up this module, you want to ask a question, please feel free to shoot in the chat, raise your hand, or just say something. Totally happy to have this be interactive. All right, so pip install diff predictor again. I think I had this happen last time. I think I just ran it again and it worked. No. So the issue that I know the issue is, and it doesn't like this old version of scikit-learn. Last time I just ran other cells and ran it. So let's import our other stuff. So we can import pandas as PD. We'll import numpy as np. We'll import matplotlib.pyplot as plt. From os import list dir get cwd and chdir. From os.path, we will import isFile and join, and then we'll import cborn as SNS. I'll try to import diff predictor from diff predictor import data process. Guessing that won't work, at least that last part, but yeah. Are other people getting the same error, or is it just me?
I'm getting the same error.
Okay. Did we get this last module and I think I just reran it and it worked. I'm confused why. Oh. So, yeah, the issue I do have the code to get around it. Just kind of bulky. I wonder. Okay, I'm just gonna try sending. Yeah, so diff predictor is a package that we developed in the Nance lab. So I'm trying to pip install it just because then we can get access to a function that I'm trying to use. But oh man, it's really not gonna let me paste in there. So in theory, pip install diff predictor would just let us have direct access to the function that collects all the data. All right, we're gonna see if we can think of a workaround. Pretty sure. All right, so we're just going to write the function out. So you can take this out for now, and we'll just do the upload those uploads, which should work. Richard, did my answer make sense about diff predictor? Because it's not really a file you need, it's like an installable package.
Yeah, that makes sense. Thanks.
Cool. Okay, so we're going to define the function instead. So I call it generate full stats. Oh, it just worked for you? Awesome. Okay. I truly don't understand why. It looks like it's going to work now. Okay, try running this cell without this, and then rerunning the pip install diff predictor, I guess. Seems like that's the solution. So yeah, I would just run all of these. And then we'll put this in a different cell. That is so strange. Thanks, Laura, for letting me know. Are other people able to also get it to pip install now after running this block of code and then running pip install by itself? Awesome. See, I just need to, this is just the line of code. Okay, so I'll leave that where it can be seen. Okay, that will make life a lot easier. Okay, so now we're going to define our path to our data. So we'll say data path equals, and then I have mine again in after mounting my drive out of content in Nance Lab, Textile, MPT data. Oops. So I'm just gonna take the easy route and copy path. And make sure to add a / at the end. And I'm gonna say my file list equals F for F in list dir data path if is file join data path F and feat in F. So again, this is just to basically go here, find all the files that actually start with feet, just to make sure we don't accidentally get anything. It's not a huge issue in Colab, but it can be an issue in other environments. And then I like to always just double check the length just to make sure I actually got all of my files. Cool. Looks like I did. Okay, so now we'll use the function that we define. So we're going to say, again, fstats tote is going to be equal to data process dot generate full stats. So we're essentially going into this module within the diff predictor package and calling this specific function. And then so we're going to pass it our data path. We're going to pass it the file list. We'll give it a list of our different ages. So again, those are P14, P35, and P70. And finally, we're going to pass it just what we want to call our target column, the variable we're really interested in. And in this case, that will be age. So we'll just make a new column for that essentially. And then we will run that. We'll get a future warning again because I have not updated using append, but that is fine. All right, have people been able to get to this point without any issues? Awesome. Cool. Okay, so we wait for it. Cool. So now I got all 75 files in. And I close the output. And similar to last time, not going to use every single feature that we have access to, just because you know, there's a lot of them, and I think it's not quite as useful to go through all of them. But we'll just look at a few. So we'll just use the same ones that I started with last time. And again, feel free to do fstats tote.column to print out the columns. What? It doesn't. No columns. And then any of them that have mean in front of it, feel free to plug those in. So I am just gonna do my features. What do I call it? Features list. Features or feature list equal to. So we'll do mean def1 mean mean alpha mean boundedness. No capital there. Mean, let's do fractal dimension. And let's do mean aspect ratio. Sure. Yeah, we'll start with that. I'm going to use those 5 again. Feel free to use any. I do highly recommend using mean def1. It's usually like the feature that has the most like importance to the data set, as we'll probably see next lecture. But I recommend at least having that one in there and then picking and choosing besides that. Okay, so then we'll now we're going to make sure we don't have any missing or 0 or infinite data in our data set. Just make sure it doesn't break anything. So I'll do ECM goes fstats tote, and then we'll just pass it our feature list, as well as our target variable, so age. And then just to make sure we remove everything, we'll do ECM equals ECM. And we want everything that is not in list. Oh no, I did that wrong. Not in ECM list set feature list. Where's the next one there? Minus, oops, no. Minus set def2 mean def2 mean def2 dot is in, and then we want to remove everything that is either numpy dot nan numpy dot inf or negative numpy dot inf. And we hope I did all my brackets right. Okay, we did not do all my brackets right. CSV dot any. I don't think that's going to solve it though. Oh, that. No, still not that. Oh, I need a square bracket here. Where did I put too many brackets? Right there. Okay, so this is always a complicated line. If you're having issues with it, you can also honestly just get around this by doing ECM equals ECM dot fill in A. And I recommend filling it with 0. So you can also do that if you want to, since this line is annoying syntax wise. So yeah, that's also a solution or an option that's totally valid. Okay, so then we want to do is we want to get a separate list of just our the age variable, so that when we go and do this unsupervised learning on it, we have a record of for each row in the data set what age it corresponded to. So we'll just call this labels, and this will be equal to numpy dot array, and it'll be ECM age. Then we're gonna do features df. So when we're doing unsupervised learning, kind of the main idea of it is instead of having our statistical features directly attached to a variable like age, we actually separate those and we train the model on the unlabeled data, so just the statistical features, and we see if we can learn any trends without knowing the different age groups or the different biological classes. And then, but then it's nice to double check to see, okay, is it actually learning like real patterns? So that's where we're going to split this into 2 groups, the labels and the features. So this is going to be equal to ECM dot drop. So we just want to remove age. And we're going to say axis equals 1 to drop it from the columns instead of the rows. Okay, so then another really important thing when doing PCA is we need to scale the data. The reason we need to scale the data is this happens a little bit in our data set, but it happens a lot for general data sets. But you could have a statistical feature that ranges between 0 and 1. You could also have one that ranges from like 1 to 1,000. And if you pass those into the model without doing anything different to the data, the model would think of 1,000 as big and 0 as small all the time, even if for a specific feature, 1 was actually really big. And so what we want to do is make sure each feature has the same basically min and max distributed between 0 and 1, so that for all of the features, the model treats every point equally, regardless of if the normal spectrum of data is really wide or really narrow. So we're going to use something called scalar equals standard scalar. I don't know if I actually imported this. I feel like I forget. Okay, I totally did forget to import this. We'll just put it here. Bad practices, but that's okay. So we're going to do from sklearn. I'm going to make sure I have sklearn installed. So if you don't know if you have it installed, I would do pip install scikit-learn. Cool. I have that installed now. Then from scikit-learn, I just usually call it sklearn. That's just convention. You don't actually need to name it out. Scikit-learn. So from sklearn dot pre-processing, we're going to import scale and standard scalar. And then we are also going to do from sklearn dot decomposition import PCA. So this is importing the actual algorithm of principal component analysis. And you can see there's some different types of it. If you want to try afterward, trying these different versions, go for it and see if you find any different results. They're just slightly different methods of performing the PCA algorithm, but we'll just do the generic one for now. Okay, cool. Now we have that. All right, so we're going to just make an object that we can use to scale the data. So scalar equals standard scalar. And then we're going to actually scale the data frame to make sure that, again, all of those features are on the same distribute or have the same min and max and the same, I think, same min, max, and mean. So we're going to do scaled data frame equals scalar. So we're just going to access this object. And we will pass, or we call the function fit transform. And so this is basically going to take the data, fit it so that, again, it fits those, that statistical criteria of being on the same distribution, and then transform the entire data set into a new one that has those aspects to it. So all the features have that distribution. So where you'll pass it our features data frame. And then this actually converts it to a NumPy array, but we want it to be a data frame just because it's easier for us to work with. So we'll just say scaled df equals pandas pd dot data frame scaled df. And then we are going to tell it that we want our columns to be equal to the feature list that we defined earlier. And run that. Cool. And so if we then take a look, let's do a look at scaled df.head. You can see that, I guess it's hard to see compared to the actual data set, but typically the mean diffusion coefficient goes a lot higher. It goes from like 0 to, I don't know, 25 plus. Now it's scaled at a much smaller level. So now we kind of have this data that is not going to be skewed when we pass it through the PCA algorithm. Okay, we are going to hop into PCA in a second. I just want to double check that everybody is good getting this point. Can you give me a thumbs up if you are able to have gotten to this point with no issues, or let me know if you run into a problem or want me to go back to a certain block of code. Oh yeah, great question. So this is just where I'm just looking at where I download my data, basically. So I knew that I was going to put my notebook into TEXTILE 2023. So then I also just uploaded my data here. And then when you do like this mount function, or this mount thing in Google Drive, then you can just kind of, I just like looked at the path I knew it was. You can also do, to help, is you can do, I think it's PWD. And so that tells me that I'm in content. So that's how I knew how to look here and then go, okay, my drive, Nance Lab, TEXTILE, MPT data. that's how I kind of went about it. And so it kind of depends on where you actually uploaded your data. Yeah, no problem. Okay, so doesn't look like no one said that anyone else has said they has had major issues. So I'm gonna jump right ahead into PCA. Okay. So the first thing we're gonna do is actually make our file list that isn't found in data path. For here. Ooh, how do you upload a folder? That's a great question. You can, I mean, if you can just like, I don't know, you can also upload all the files individually. I don't know. I was able to just directly upload a folder when I went into my Google Drive. But even if you did just upload all the files individually, then you could still use this part of it to get just the feature files from that folder. Oops, I think what I did was I just had the option to upload it to do a folder upload. So that's what I did. So what is it? Is it not finding like this data path that you're trying to put in?
No, it's finding that. It's just saying that file list isn't found in the path.
Okay. So file list is a variable that we're defining. So not really sure.
Oh wait, never mind. It's saying that the path isn't a directory.
Isn't a directory. Oh, okay.
Yeah.
Did you make sure to have like a backslash here?
Oh yeah, forgot that.
Yeah, I had so the issue with uploading a zip file is I don't think you can unzip it directly in Google Drive. So what I did, I think so I shared it as a zip file. So what I did was I unzipped the file and then just uploaded those directly. So I don't know if you can from a zip, zip. I don't think that you can unzip in the Google Doc or the Google Drive folder directly. I can also we'll get to a point soon where it's going to be a little more like have time for people to spend playing around with plots. So I can totally hop into like a breakout room and we can figure out the file thing if you want. Yes, totally. Features DF. Think I did it here. So this is how I define features DF. So I just used like the dot drop function and just told it to drop age, and then we need the axis equals 1. Otherwise, I think it will. I forget I think the default is 0, which means we'll try to drop it from a row. And so this just makes sure that we drop it as a column, not as a row. Yeah, it might just be a location issue. Okay. So let's make a PCA. I guess it's an object. Let's start creating the PCA algorithm. So we'll say PCA equals PCA, and we're gonna say number of components. So this is how many features we actually want to have the algorithm shrink it down to. So I'm gonna just start with 10, but you can feel free to try out however many you want. Do at least 2 probably. But you can also, nice thing is if you do 14 versus 2, it's still like if you just do 2 and I do 14, our 2 are still going to be basically the same. It just only will return the first 2, so there's no harm in doing more. It's still each slice, each like principal component is going to be the same, as we'll see. So then we're going to do dot fit, and we're going to pass it the scaled data frame. Why is that giving me there? I don't know. So then we're going to print out the results, and we're going to print out the explained variance ratio. And then we're going to say, and this has like a little underscore after it, because this is like an innate variable of PCA. And then we're going to call dot sum on that just to sum it all together. And it's going to throw must be routine. I forgot that I only had five components. So we're going to reduce ours just down to 2. And you can see that we explain 60% of the variance. So this is saying that in the first 2 components of the data that's been shrunk down, 60% of the variance of the data is explained by that. So we're capturing a pretty big portion of it. Are capturing 60% of the data in just 2 features, which is pretty cool. And usually when you have, if we put in a lot of features here, this gets a lot higher. And with just a few features, you can capture a lot of different, a lot of the variance. We can also do is make a plot to look at this. So we'll do plt.plot, use the numpy cumulative summation function. And then we're going to do pass, or just give it the explained variance ratio. And then we're just going to do an X label, which is the number of components. And then we'll do the Y label, which is the cumulative explained variance. What did I do wrong? Okay. Ratio, not ration. Okay, well, interesting. It's linear. So usually, wait, why is it going? Surprised it's counting. That's kind of weird. But so what's kind of happening here is it's showing. Why is it going up to? All right, we're gonna put this up to 4. So you can see with 4 features, it captures 93% of the variance. That makes a lot of sense because we only have 5 features. So it makes sense that in 4 of them, if we distill it, 4 is going to have most of it. But the main thing I want to show here is that what this does, which is cool, is you can see that just this first one, it gets us up to almost 60% of the variance, right? So this first component, the first thing we shrink it down to is almost 60% of the variance. Going up to 2 jumps it even higher, and 3 gets it all the way up. And so, but so this is like useful, but the really powerful thing we can do with this is making like actual plots of each of the data point from each different class. And so that's what we're going to do next. This is nice to show that it is increasing, and then that there is a little bit of plateau. But the next part is kind of like one of the main ways that PCA gets used. So we're going to do PCA embeddings is going to be equal to PCA dot transform scaled data frame. So this is just getting out specific aspects of the PCA algorithm or the results of it. So this is just giving us for each of the different rows, how much of their for each, like how much is explained is each of them for each of the different principal components. So then we're going to make a data frame out of this to make it easier to work with. So PCA embeddings data frame equals pandas dot data frame PCA underscore embeddings. Then we're going to say we want all of the rows and then we'll just say that we want the first two columns. I guess would that be so 0, that'd be 0 to 2. And then we're gonna say that we're gonna want to name the columns. What did I do wrong? Oh no. That is gonna go. Oh, nope. Data frame, PCA. No, we don't need a colon here or parentheses there. So we'll name the columns PCA1. Here also is PC1 for principal component 1 and principal component 2. Oh, sorry, columns equals. So that should work. And then we are then going to figure out or kind of reassociate each row with the age group it came from. So again, we've trained this model with it not having access to the age data. We want to see if it doesn't have access to the age data, it has access only to the unlabeled data, can it still learn some patterns? So we'll call this, we'll say PCA embeddings data frame, and we'll make this new column called target. So that's just going to be our age variable. And we'll set that equal to labels since we used that before. And then cool. Okay. So then we're going to make the plot, and after we get to this point, we're going to start going a little bit into getting to play around with different features and stuff. So this will be a little bit more interactive after this, I hope. But what we'll do is we're going to make a new matplotlib figure. PLT equals PLT dot figure fig size equals, I'm gonna do 12 and 7. We'll see how that ends up looking. Okay, so then we're gonna do, now we want to kind of loop through each of the different age groups and plot them in different colors so we can actually see the distribution of the data and if the model picked up any patterns. So we'll say for unique class in PCA embeddings df target dot unique. So this is just going to make a list of our three age groups, and we'll colon at the end. We'll say that our data frame equals PCA embeddings df, and then we'll do it again, PCA embeddings df target. So we're going to look at just at the target column for a second, and then see if it's equal to the unique class that we're currently looking at in our for loop. And we're going to say our x values is going to be equal to this data frame. Again, so this data frame is just a subset of one age, and then this is going to be PC1, so our first principal component column that captures a lot of the variance. Our y is going to be equal to data frame PC2. And then we are going to do a scatter plot. So plt.scatter, scatter x, y. I'm going to say alpha equal to 0.5. This is like how opaque each point is. So you can play around with this. Size of each data point is equal to 4. And I'm going to do a label. It's going to be equal to the unique class that we're using. Oops, label. Okay. Then just to make the plot look a little nicer, we're going to do plt.legend. We'll do plt.xlim. Actually, we'll skip that for now. We'll see that should be later. We'll do plt.xlabel, and we'll say PC1, plt.ylabel, label. PC2. And we'll do a title. So plt.title first and second principal components. And I hope it works. Cool, it did work. I'm gonna change the size of that. Maybe, I don't even know if that'll work. It's a little nicer. Okay, so cool. It seems like it worked. And so what we're seeing here is that each of the different colors are a different age group. And so this is kind of showing us what we want. What we wouldn't want to see, although what you've seen a little bit, is that there's a lot of overlap between the data. This is honestly just kind of happening because we only are capturing 60% of the variance, just because we're only using a few features in the data set. But we can see that there are somewhat distinct clusters. So we have this green cluster that is a little more up and to the right. We have, and so that's the age 14 data. We have this middle P35 data that's kind of centered compared to the other two, and P14 that's a little bit lower. One thing you can also do if you want to, I don't know, make the plot a little more clear, you can reduce the opacity and the size. You can also do, I think it's here, you can do dot sample. And so this is going to take a subset of the data. So we'll just set it to 100 points. And then, oh wow, that went really light. Okay, that's lighter than I was hoping to be. We'll go back to this. But now by looking at only 100 points for each data class, we can kind of get a better sense of if they are separated from each other or not. And here you can kind of see better this separation of green being having the points be higher, P35 being in the middle, and P14 being lowest. And so one thing that's interesting about PCA is these values, they don't actually mean anything. I mean, they do in the sense that like they represent each data point properly, but a value of 0 versus a value of 4, those don't actually tie back to our original data set because they are data that has been transformed to capture variance. So saying -2 or 2 doesn't really mean anything in the sense of it connecting back to biological data. So this is really more for just representing the data and seeing if there is any patterns or any spread between data classes here. Okay, let's see. One other plot I'm going to introduce, and then we'll get a little more interactive, is going to be a 3-dimensional plot. And I really like these. So I think we have, I'm going to make sure, PCA, embeddings, DF. We should add one more, shouldn't we? Okay, so we're going to go, so I go up to this line, go out to 3, and then we're going to say principal component 3. Cool, so we have a third one now. And as you'll see here, the plot's going to look essentially the same. It looks a little different because the random sample is different. But even though we have 3 principal components now versus 2, right, this hasn't really changed because that third component was always there. We just weren't plotting it before. It was still calculated. Okay, so what we're going to do is we're going to say our x-axis is going to be equal to PCA embeddings. So we're going to say we want all of the rows again, and just the first column. Our y-axis is going to be equal to PCA embeddings. Just that column. Am I doing this right? I think yeah, okay. Yeah, PCA embeddings 1, and then z-axis equal to PCA embeddings. Oops. All the rows, third column. Column 1. There we go. And then we are going to make a new figure. So figure equals PLT dot fig size equals 8,4 again. 8,4. Our ax is going to be equal to fig dot add subplots 1, 1, 1. Projection equals 3D. So this is how we actually make it so we can make a 3-dimensional plot. We're going to basically just go up here, steal this chunk of code again. I don't really want to rewrite it. Again, not the best practice, but it's okay. And then the one change we'll make here is that we're going to say z equals df pc 3. And then we're going to change this as well. So instead of plt.x.scatter, we'll do ax.scatter, and we will do x, y, and z this time. Okay, I'm just going to make sure that this actually no figure. What? They may have changed the documentation since I last did this, which would be unfortunate. Oh, no, I think I spelled it wrong. Whew, okay, good. That's good. So now we have this 3-dimensional plot. And so there's some stuff we can do to make it, again, make it nicer. So we can do, let's do an ax.legend, and let's just try that for now. So yeah, I think this also is one that would benefit from, oh, why did that make it so different? Interesting. Also playing around with the sample can be really nice, just to make sure it's there. So yeah, this is another really cool way I like to visualize them. So instead of just having in 2 dimensions, we can get a 3-dimensional sense of it. There are more advanced options you can do with this type of plot to make it able to rotate, which is really nice. But again, this does kind of show us that using these 3 components, we can get a better sense of where and how these plots are separated. Yeah. Another thing that I believe we can do, this is another way I like to make these 3D plots, is can do fig equals plt dot scatter 3D. I believe this is the function. PCA embeddings df. You can say our x equals PC1, our y equals PC2, and our z equals PC3. We'll say color equals PCA embeddings df target, and we will, oops, oh no. Maybe that doesn't exist anymore. Okay, this one might not work anymore. Or if it does, I will figure out for next month. We'll talk about it. Okay, so now that we have these 2 different methods of plotting principal components, what I would like y'all to do is hop back up to this feature list. And again, you can do feature fstatstos.columns to get different statistical features. You could definitely try playing around with just non-mean ones, just like dfit. You could try standard deviation. I don't expect those to have a lot of valuable information in them, but feel free to try. So then try adding some more here, get up to like 10 or 12, and then go through the same process and specifically scale it and look at the cumulative summation. And then where did I? and do the actual piece, the component fitting, and see if by adding features, you can get to, when you do PC, let's say when you do PC equals 2, see if you can find something, or PC equals 2, oops, find some combination that gets higher than 60%. And then if you can, and then see if you can see any changes in the distribution. Here in the previous cell. This, I'm assuming the cell before feature list. This in the cell. Oh, the 3D figure. Gotcha. Yeah. Okay. I'm gonna make a breakout room really quick. I'm guessing this will stop my screen share, but I'm gonna quickly open this room. I'm gonna hop into it for a couple minutes. If people have specific questions, feel free to hop into here, and we can try to figure them out. If not, again, this is gonna be recorded, so it's not the end of the world, but I would love to get it working. So yeah, in the meantime, if you don't have any questions, feel free to play around with those different features and see if you can make some plots that capture the spread of the data more than just the 5 that I did. Let me start recording again and sharing my screen again. Okay. There we go. Share screen. Okay, awesome. Did anybody find any interesting combinations of features that they want me to, that they would like me to try, that found some cool variants or found some, captured a lot of the variants of the data? Oops. All right, well, let's see what happens if I'm gonna try to toss in much bigger subset of the features. So don't feel the need to copy this in. I am not going to type this all in. This is just something I already have saved. So this is all of the potential features we have. So I think it's like 33. So we'll put that in. We'll do our normal process. We already have scikit-learn installed, which is great. sklearn, scale data frame. Cool. So now we have all these features this time. And so let's see what we get with 2 components. See if we get higher than 60. Again, it takes a little longer just because it's calculating on a bunch more statistical features. Oh, wow, that's really bad. Okay, so with 2 features, I mean, this is part of it is just because there's a ton of features. And so there's just more variants to try to capture. But to 2 components, we only are actually getting 36% of the data. I'm going to try, if I take out the non-mean values, will that make it better? Okay, that makes it a little bit better. So with 2, we get 50% of the variance. And considering we're doing like 15 features and reducing down to 2, that's actually pretty good. With just 2 features, we're capturing features on the variance across 15 features. Hopefully this plot will look a little better now that we have more. Oh, no, it is not. Oh, right, I need to, let's go up to 10. So again, with 10, we capture 96% on the variance, which makes a lot of sense. But here we can see that there's kind of this plateau that initially is pretty linear. Get 1, we get a really big increase, or I guess 0, that's where it starts, then 1, and 2, and so we kind of start getting this is where it's really, these ones capture the most of the variance, and these remaining ones capture less, which makes sense because in principal components, the goal is to have the first component capture the most variance, the second one capture the second. I think we could do here actually is do. So our first principal component captures 30%. Our second one captures 20%. So that's how we get to 50. Our third one only captures, wait, no, I forgot we need to index properly. Oh yeah, 15%, and then 7. So you can see it pretty rapidly. We start to get this decrease that is the same as, that's basically being represented by this plot as well. Okay, so let's then try to make some of our plots and see if they look any different. So to me, what really stands out here is if we add all the data in, we get a little bit better separation actually of the P14 age class, but we get a worse separation of the P70 and the P30. And this is actually really informative because, and we'll explore a little bit more next time, but this is kind of showing that the model is picking up that like there is a pretty clear distinction between P14 data or data like trajectories from a P14 age brain compared to the other two, but there's not a really big difference between P70 and P35. So one thing to think about as we're going into our next supervised machine learning model is if can these models actually differentiate between these two classes within each other, because our PCA is showing that their data is actually really, really similar when we plot them. Let's see how these look with the 3D plots as well. So I think it looks pretty similar to before, but we can kind of see in 3 dimensions, right? We go from these being overlapping a lot to I think having a better or having less overlap, having more clear separation. So we can see that, you know, maybe there's a lot of overlap within 2 dimensions, but once we add a 3rd dimension, we do get a much better visualization. The other really powerful, what are some common ways to visualize variance? Do you use box and whisker plots often? Yeah, totally. I like box and whisker plots with that. So again, the kind of difference here though is box and whisker plots are really good for a single feature, statistical feature, but it's hard. I guess you could theoretically do them for every single feature, but once we have like 30 features, that gets really difficult. And so that's really the power of doing PCA. It's not just it's looking at variance across the entirety of the data set at once, rather than combing through specific aspects of it. But I think this actually highlights a really good point of where we do want to be able to take these plots and be like, okay, there is some data spread, but what's driving that data spread? And then can we visualize those variants using box and whisker plots, using violin plots individually. So another really powerful thing about PCA is that you can actually see which statistical features are driving the most separation in the data. So we're going to make a new function to do that. So we're going to call this def biplot. I'm not sure why it's called a biplot. That's just what it's known as when I've looked up on Wikipedia when I try to figure out how to do these plots. And we are going to pass it, let's see. This is going to be somewhat a bulky function, but I think the plot is pretty cool. So we're going to pass it an argument called score, one called coef, one called labels, which we're going to set to none equal initially. Targets, Again, we're going to set this to none, and then number of points. And I'm going to set the default equal to equals all. All right, so there's our initial function. So we're then going to make a variable called x's, which is going to be equal to score. And this is going to take all of the rows and just the first column. Do our y's, which will be equal to the score we pass it, and all the rows, and just the second column. Oops, I guess nth column. We'll do that n equals coef dot shape 0. We're going to do scale x equals 1.0, and then we're going to divide this by the xs dot max, so the maximum value there, minus the xs dot min. And we're going to do the same thing for y. So scale y equals 1.0 divided by, did I have? Yes, okay, did that right. Y's max minus y's dot min. Scale y. There we go. Okay, so then we're going to do kind of something similar by cycling through the unique classes. So we'll say for unique class, I'm just going to call it U class in numpy dot unique targets, our x value will be equal to the x's, where the targets are equal to the U class, multiplied by this scaling factor we just created. Our y is going to be equal to, all of these need to be in a parentheses. So then y's targets equals U class, multiplied by the same scaling factor. And then I'm going to say if num points equals all, and this is just a nice thing that makes the function a little more usable. So we can either choose to do all the points or kind of that sample thing we did earlier, where we can do like 100 or 500 instead of all the data points. So if num points equals all, we'll just do plt dot scatter x, y, say alpha equals 0.5 and size equals 1. Else, we will do the index of the points we want to plot will be numpy dot random dot rand int 0 len of x. So this is just telling us how much we actually want to do, and then num points. So what this is going to do is choose a random number between a random list of indexes between 0 and the length of the data set we're going to pass it, and choose this whatever points you pass through out of there as the points that are going to be there. So again, just completely randomly sampling the data, so that we can make a nicer visual, and so but still get like a random, so less biased estimate of the distribution. And we'll do the same thing for the scatter. So plt dot scatter x, but we'll just do x of indexes, y of the indexes, and we'll do alpha equals 0.5 and s equals 1. Okay, then we'll back out and align with the for loop again. All right, so this now we're going to do the actual, I guess this is basically just going to make the PCA plots. but now we're gonna do the part that adds kind of the complexity in, or it adds like this extra piece to it. So we're gonna do for I in range n 2/2 n. Put those in. I don't think you actually need those parentheses, but better to be safe. And we're gonna do a new matplotlib function, I think, called, or new, I don't think we've used this one before, but plt.arrow. So just literally it's gonna draw an arrow with 0, 0. So those are the center coordinates. And then to coef I 0. And then coef I 1. Then we'll add some, just again, stuff to make it look nicer. So we'll say the color is going to be equal to red. You can totally change this to whatever you want. What your arrow colors to be. Alpha equals 0.5. And then we'll do, let's see, plt.text. So you can do a coef I 0 multiplied by 1.15. To be honest, I don't know where the 1.15 comes from. This is just the template function I found when I did this had it, and I think it's just to make the text we're gonna have on here a nicer size. Coef I 1 times 1.15, 6.5. And then we're going to say var plus str I plus 1. And then color equals k, which is the k represents, we'll color it black. HA equals center, and VA equals center. So I think that's horizontal axis and vertical axis. Oops. Okay, and then we'll do, all right, well, let's make sure this works first before I add some labels and stuff. Okay, so what we're gonna do now is we're gonna make a new figure. So figure equals plt.figure, big size equals, let's do 12 and 8. 12, 8. And we're gonna call biplot. And then we're gonna pass it our PCA embeddings. And then we're gonna give it in brackets, we're gonna just give it all the rows, and then just 0 to 2. And then we are going to pass it numpy.transpose pca.components. Make sure this has a little underscore again at the end, just to give it that specific tie it specifically to the PCA variable that it itself has stored. And then it's going to be 0 to 2. 0 to 2, and then all of the rows, but it's transposed, so it's actually flipping our rows and columns. It's going to flip those, and that's why this here is opposite, or like these 0 to 2 here, and then the colon versus colon is 0 to 2. And then we'll say that our labels are equal to the feature list. Our targets are equal to our labels. That is kind of weird wording there, but bear with me. And then num points, and again, you can set this to, if you don't set this, it will just be all I think that will get messy, and so I'm going to do, let's do 200. And let's see if this runs. No, okay. Got unexpected. Really? Ah, I see what happened. Take out one of these back two and put it here. And then that should work. Oh my gosh, that is long. Okay. 12-8 was the wrong choice. We'll do 8, 8, 4. Oh my gosh, am I in the breakout room still? No, I don't think I hope not.
Yeah, we're in the breakout room, I think.
Oh, that is embarrassing. Can other people see this or no?
I think only people in the breakout room can see this, and there's like 5 people in this breakout room right now.
I think Laura, I think that's everybody though. I think we're back in the main room.
No, I can still click leave breakout room on my screen.
Oh, really?
Yeah.
Oh, interesting.
Yeah,
Looks
I
like
think
everybody
everyone
did
joined.
everybody just join this? Okay, I'm just gonna close this room. Sorry about that, everybody. Laura, did you see the stuff I've been doing with the plot?
Yeah.
Okay. All right. Well, hopefully this works. Do I need to share again? Oh no, it should still recording. Okay, cool. Did people see me go walk through this code, or did only a few people see that? Can you give me a thumbs up if you did see me walk through it? Okay, cool. I think it was recorded too, so worst case should still be up there. Okay. Let's thank you for letting me know that though, Amber. Okay, that looks a little bit. This honestly, I've never been good at figuring out how to make this plot look super nice, but the idea here is that actually I'm gonna quickly change one part of this to make it make more sense. All right, so in this section, in the this last line, we're gonna change it to. I'm gonna take out the 1.15, and we're gonna take out. No, we're just gonna take out this part. So coef. We're gonna pass it labels I. And what I'm hoping this does is, well, one work. Okay, cool. So now we can see what it shows is which of the statistical features in the data set are actually driving the different age groups we have to be different from one another. So the way you can read this is, and of course these are directly overlap, but I believe that's mean trappedness and mean boundedness, is that mean diffusion, the mean def1, mean straightness, and mean efficiency are the main statistical features that are driving data points to be up in the top right corner, versus mean fractal dimension is driving data points to be closer to the lower left corner. Mean trappedness and mean boundedness are ones that are driving differentiation in this direction. And the mean diffusion coefficient 2 and mean square disk ratio are in this direction. So the length and the direction are the show kind of like the magnitude and the actual direction that features are pulling. So this is really nice because we can now see, kind of similar to before, we still see that there is this age class here that seems different from these two, but now we can start getting some insights into why they are different. And this is one of, I think, the really powerful parts of unsupervised learning and machine learning in general, but this especially this technique of a supervised learning, a PCA, is that we can start to understand not just that there are differences between different ages, different biological conditions within the data set, but we can start to pinpoint which actual features that we measure are causing the difference. So yeah, haven't honestly figured out how to do it with 3D, although that would be pretty cool, but perhaps just really confusing. But this is one thing I really like to do when I'm looking at data set for the first time, is to see what's actually driving data. And this is going to actually be really, really informative for us when we jump into supervised learning and building models that do train between a row in the data set and a label. So instead of unlabeled data like PCA, next time we're going to talk about training models that do know that relationship between these statistical features and the age. Okay, so I think we're right about 80 minutes, which is perfect, right where I wanted to be. Yeah, cool. So yeah, I just kind of in this module, my goal is really to show you some of the unsupervised learning techniques that I like to use and we use in MPT to get plots to understand our data. So yeah, thank you all for coming out and listening. Again, if you want to go back over stuff, they'll be recorded. And sorry for not having the pre-module ready. I think if you watch the PCA video, what each actual data point means might make a little more sense, but I hope that you kind of got the idea that we are going from this really big data set of what is it, ECM dot columns. We're going from this data set that has all of these features that are potentially causing differences in our age variable, but we can't, it's hard to visualize them all individually like we did last module. But now we can put them all into this algorithm and get plots out that show specifically which ones are really important for the differences and how the data is separated from each other. So yeah, I think that's all I have today. If anybody has questions, let me know. But otherwise, thanks for being here.
Bye. Thank you.
I
Thank
have
you.
a question on like the ECM one. It keeps showing an error, like after I checked it, and I don't think I got like anything typed incorrectly.
Okay. Do you want to share your screen again? Would that be okay?
Yeah, I can.